Well, welcome to the presidential series lecture by Sassan Karimi. Before I introduce Dr. Karimi, let me tell you a little bit about presidential lectures and the purpose of this type of activity. It is very easy for teaching institutions, and community colleges are clearly teaching institutions, to fall into the routine of just going to the classes, teaching the lectures, doing the work, and then not following with other activities. And it is very easy in teaching institutions, and really in any institution, for faculty, administration, and the community to sort of feel isolated. You know, people stay in their disciplines and talk to each other within the disciplines, but there's rarely a time that we can have an exchange across disciplines and the college and the community at large. So about 5 years ago, a group of members of our faculty and staff created a committee. And I'd like to ask the members of the committee who are here. I don't know if Gillespie is here. Who else is here? Peter Gray is here. Please stand up and be recognized. Okay, so there's only two members of the committee who are here. Came up with the idea of having these presidential lectures. And the idea is to have a celebration of our faculty, not only across the university, but within our institution. So in the fall, we have a lecture that is dedicated to the university at large, and we generally have someone who is either a distinguished professor or somebody who is a luminary within the university, but not from Queensborough. And in the spring, we reserve this time for a member of our staff who is a distinguished member of our college community. And the purpose of the lectures are to be open community-type lectures about issues that they feel are important and issues that might be interesting to the community at large. So it is an intellectual activity, and it's a way that we have sharing with the community the good work that is being done at Queensborough. So I am delighted that this program continues to grow, and I am delighted that the attendance, some of you are always at these lectures, and I think that that is a wonderful sign that we are producing a good product. Today we have a special treatment. Sassan Karimi has a Ph.D. in organic chemistry from the Graduate Center from the City University of New York. I don't know how many of you have taken organic chemistry. I have. And it is not an easy subject. As a matter of fact, it's usually a watershed subject for biologists. So he is a synthetic organic chemist. And that's almost an oxymoron, right? Because organic means anything that has carbon, anything that's life. But he is a synthetic organic chemistry. And he's been with us for 7 years. And one of the things that is really interesting about his work and his work at QCC is that he has mentored a large number of research students. Now, something special is happening at the chemistry department at Queensborough. And what I believe is very special is the fact that our faculty truly believes that freshmen and sophomores in a collegiate experience are capable of doing original research. Now that's sometimes it's hard to believe, because those of you and those of us who have been in the laboratory know that the norm is that you went to your graduate school to be able to do some original research. And it's very rare that an undergraduate can do that. In this department, something is happening, that a number of individuals have believed in their students to such an extent that they have encouraged them to do individual research. And, you know, we have had our students presenting at the American Chemical Association meetings. We have had a conference here where we had individuals from all over Long Island, as a Long Island chapter, presenting individual and original work at our institution. Dr. Karimi has a number of peer research journals. He has almost over 20 peer-reviewed scientific articles and more than 50 presentations in national scientific conferences and symposia. There's also been a recipient of over 12 grants in chemistry, both from CUNY and external agencies. What is interesting about today's lecture is that Dr. Karimi is an individual who has been interested in the chemistry of art, and they have created this course that is truly interdisciplinary. How many times do you think about chemistry and art coming together? Well, it happens here, and it happens very successfully. And for one, I am very interested in seeing what is done with the course, with the field, and I am excited about presenting to you one of our own, one of our best, Dr. Sassan Karimi.
Can you hear me? Well, thank you, Dr. Marty, for the introduction and the opportunity to be the speaker for the 2006 Presidential Lecture Series. Today, well, that's the title of my talk, but before I begin my talk officially, I'd like to just point out to some of the differences between how scientists perform their research. So, one day, a physicist, biologist, and chemist went to the ocean for the first time, and the physicist saw the ocean and was fascinated by the waves, so he decided to do his research on the fluid dynamics and walked into the ocean and was drowned. Later, the biologist decided to do his research on the plant and microorganisms. He too walked into the ocean and was drowned. And the chemist was watching all this happen and took a long time.
Can't hear you when you turn away from us, sir.
Sorry. Can you hear me now?
Yes. But if you turn away.
So the chemist took a long time and finally wrote in his observation that both the physicists and the biologists are soluble in water. The first part of my talk is in two parts. The first part I'm going to talk about some of the wonderful things that's going on in the chemistry department as far as engaging the students into conducting research. These students have aspirations in going to pre-med or dental school or pharmacy school, or they want to become physician assistant or physical therapy or some other health allied field. The second part of my lecture will focus on how we teach chemistry for non-science majors, particularly those, I'm going to speak specifically about a course that I developed a number of years ago, the Chemistry and the Arts, Chemistry 103 and 104. Before I begin any of these two topics, I'd just like to briefly tell you what chemistry actually is. Chemistry is a science that studies the properties of substances and the changes that it undergoes. Chemists are primarily concerned with natural substances, that is the minerals of the earth, gases of the air, water and the salts of the seas, living creatures, and they're also interested in creating new substances. Chemists like to believe that chemistry is in fact a central science because it impacts so many disciplines. For example, it makes contributions to medicine, biology, physics, geology, agriculture, and archaeology, to name a few. And the type of questions chemists ask is how can we improve the quality of human life using different properties of substances, such as making new medicine, new construction material, or new clothing. Here I have listed some of the disciplines in chemistry: organic, inorganic, physical, analytical, and biochemistry. There are other subdisciplines that can be derived from any possible combination of these disciplines, namely bioorganic, bioinorganic, physical organic, or physical inorganic chemistry. My area of focus is in the area of organic chemistry, and the art and science of organic chemistry has characteristics both of building a house, that is to construct a predefined structure, and it's also similar to exploring a continent in that it requires a successful traverse into some unknown territory and sometimes formidable barriers. To make a complex organic molecule poses several challenges. One is to make a correct structure, and the other one is finding a way to get there. One of the major sources of new medicines is found in natural products, substances that are extracted or isolated from living things, such as marine organisms, microorganisms such as fungi or bacteria, snake venom, tree bark, leaves, and other plant sources. There are literally thousands of substances that are isolated each year, but only a very few, are found to be potentially useful medicinal substances, as crucial as a cure for cancer or as useful as a headache medicine. I promise not to show you a lot of complicated. Can you hear me? Can you hear me now? Yes. As I was saying, I promise not to show you a lot of complicated chemical structures today, but this one is certainly worth mentioning. This compound represents Taxol. It was initially extracted from the Pacific yew tree, and it's supposed to be one of the most reactive anti-cancer drugs that are given to patients with very advanced ovarian and breast cancer. Unfortunately, the nature doesn't make a large quantity of this compound to suffice all the patients. So it becomes a task of an organic chemist to make this compound or to contemplate or envision a synthetic methodology to make this compound from relatively simple starting material. But the challenge is to finding the simplest way of making this complicated molecule is actually quite often very difficult. And in the case of Taxol, it may involve 30 or 40 synthetic steps. In my lab, I work with much easier looking molecule than Taxol, but I would say still quite challenging to synthesize. With the aid of students at Queensborough over the years, I've been able to synthesize the following natural products: sadovine, longifloline, and copine. The results of our investigations have been published in journals of natural products, and as early as a few months ago in the Journal of Synthetic Communication. Some of the applications of these compounds are also known. For example, longifloline happens to have some antifungal and antibacterial activity. Some of the derivatives of sadovine are actually used as plant growth hormone, and some of the related compounds to copine are used as resins in varnishes. Our synthetic method towards the synthesis of the two natural products, sadovine and longifloline, starts out with a relatively simple and commercially available starting material. What differs is the synthetic methodology of converting this simple compound to this complicated molecule and the number of steps during their transformation. To make sadovine, for instance, it took us 9 synthetic steps to make, and to make longifloline, it required 13 steps. The structure of copine was achieved in only 4 steps. The student who was involved in the longifloline project is Paula Tavares, who's standing to my left in the picture, and she took organic chemistry with Professor Spranos, our chemistry department, and she decided to do research with me in the lab at Queen's College. And she was such a terrific student that I recall when I was writing the article on the longifloline chemistry, she was conducting the most sophisticated chemical synthesis all on her own with very little assistance. I'm happy to report that she's presently working at the OSI pharmaceutical company and doing very, very well. This is Julia Christodoulou, who worked on the copine project, and she is graduating. She also graduated from Queensborough and is graduating from Queen's College this June. This is one of the success stories at Queensborough. Dr. Jane Rizzo, who graduated from Queensborough in 1996 and earned her BS, Master's, and Ph.D. from Queen's College and completed in the year 2001. She is now an associate professor of organic chemistry at Pace University, and our department is very pleased with her accomplishments. These projects are primarily done at various places such as QCC or some of the other four-year institutions, CUNY institutions. I do my research at Queens College, and several of the other faculty do their research also at Queens and the College of Staten Island. Some of our faculty also supervise student research in some of the chemical industries, such as the Brookhaven National Lab, the Food and Drug Administration, and the Mount Sinai. The results of the students' projects are presented either through poster or oral presentation at Sigma Xi, which is a student honor society, or nationally at the American Chemical Society conferences, or regionally at the Mid-Atlantic meeting, or locally at the ACS Undergraduate Research Symposium, one of which we hosted. Here is a picture of all the student presenters and their mentors, as well as some of the family members. And the keynote speaker for the event was the Nobel Prize winner, Dr. John Knapp. Here are selected publications of our work with students from Queensborough, and several of these works have been possible from some internal collaboration. The third one down here, for instance, involved one of my collaboration with Professor Humorous that led into publication in the Tetrahedron letter. And I'm also proud of another collaboration that we do externally involving students with Professor James Canary from New York University and Dr. Nino Baroa from Columbia University. That work was published in the Journal of the American Chemical Society, which is a chemist, one of the most prestigious journals in chemistry. What we try to accomplish with science students is actually for them to grasp a conceptual understanding of the chemistry projects that they do. This way, when they leave Queensborough, they leave with a meaningful research experience. We also hope that they improve on their problem-solving skills so that they realize that there may be more than one solution to a problem. Working in a laboratory-based research brings about a closer faculty-student interaction, and public presentation evokes a sense of accomplishment for the students that they realize that they are just as good as students in a four-year institution. We're also interested in retention. Therefore, by engaging them in research early enough, we will encourage them to stay with us until they graduate. Well, this was the first part of the talk, and the second part is going to be about the course that I developed a number of years ago, Chemistry and the Arts. It was designed for non-science majors, specifically for those in the art and photography. The course is intended to introduce students to the relevance of chemistry, that is, having a background in chemistry to provide them with a fundamental understanding of the materials that are used in the arts. And there is also more emphasis on the practical contributions of chemistry, and the more mathematical and theoretical aspect of it is not as accentuated. Here are some of the objectives that we hope to achieve with teaching this course: is to introduce students to a scientific study of the materials used in the construction of work of art. So we include some of the materials, such as organic and inorganic material, in these lectures. We also like the students to become familiarized and learn how to use scientific instruments, such as infrared and ultraviolet visible spectroscopy. Some techniques in chromatography and other methods of chemical investigations will be employed in order to examine the physical and the chemical properties of substances. We also hope that another very important objective for us is the students hopefully will become familiarized with how to properly and safely dispose and handle potentially hazardous substances that they use in their daily operations. Preparing, manufacturing, identifying compounds such as dyes, paints, and pigments will entice the students into thinking how the old artists used to actually synthesize their own pigments and grind them into their own appropriate particle size in order to control the grade of their final product. Here is a list of topics that are covered in the course. We begin the course by an introduction to light and color, followed by some topics on primary colors of pigment versus the primary colors of light and their additive and subtractive mixing properties. It is, after all, a chemistry class, so they will learn how to recognize the chemical structures of dyes, fibers, pigments, adhesives, media such as oil, acrylics, and we also discuss the chemistry of black and white photography, and several lectures are devoted to art conservation and detection of forgeries. So I'm going to take you through the course, if you bear with me. I promise not to bore you. We begin the course with an introduction to light and its refraction properties. And we use Isaac Newton's first experiment by essentially sending ordinary sunlight through a prism and dispersing it into its constituent colors: red, orange, yellow, green, blue, indigo, and violet. This is a refraction property of the light, and that is because each color of light, having different energies, are bent slightly at a different angle. Now, the visible colors, namely the red, orange, yellow, green, blue, indigo, and violet, which we call Roy G. Biv, only constitutes a very narrow region of the entire electromagnetic radiation, covering from 400 to 700 nanometers. When we introduce light and its property, we then like to find out what happens as a result of the interaction of light with the object. So we ask questions like, can you name 3 things that occur when light strikes an object? Students answer: reflection, absorption, and transmission. Another question is asked: clear glass, water, and air are examples of what kind of compound? Transparent. That's when all the wavelengths of visible light are transmitted through the object. An additional question is asked: what would be an example of reflection? A white opaque object where it reflects all the wavelengths of the visible light, as opposed to a black object where it absorbs all the wavelengths of the visible light. There are objects that appear to be colored, such as this green object, where it absorbs most of the wavelengths of the visible light, with the exception of the green, which is reflected back to your eyes. We then emphasize on the additive properties of the primary colors of light, namely red, green, and the blue. So what would happen if you superimpose a blue light on a red light? You produce magenta, right? When you overlap red with a green light, you produce green, yellow, and then when you superimpose blue and green, you get cyan. When you overlap all the primary colors of light on the same spot, it will appear as white. Now, the property of the additive mixing of the primary colors of light was actually employed by the French Impressionists in general, and the neo-impressionists like Georges Seurat in particular. Georges Seurat invented a method of painting called pointillism, where he painted tiny dots of colors adjacent to one another, and then when the work of art was viewed from a distance, the colors underwent additive mixing due to spatial averaging and vision persistence. And these artists also use spurts of pure color that spatially average to clear, brilliant hues that ultimately make the pigments look brighter. We then talk about the subtractive colors and make sure that the students realize the difference between the primary colors of pigment as opposed to the primary colors of light. As the artists point out, the primary colors of pigments are yellow, cyan, and magenta, but their mixing properties are not additive, but they are subtractive. For example, when you overlap the primary color of pigments such as cyan with magenta, the result will be blue, and overlapping cyan with yellow produces red, and overlapping yellow with cyan produces green. Now mixing all these primary colors of pigment in equal proportion produces black, and essentially as we add more and more of the primary colors of pigment, we're subtracting more and more from the visible spectrum, and there is less which is reflected back to your eyes, and that's why it appears as black. Also notice that each primary colors of pigment reflects the two pure color they intersect. For example, cyan reflects blue and green, magenta reflects blue and red, yellow reflects red and green. These graphs illustrate the subtractive mixing of the primary colors of pigment. And when we examine an artist's blue paint and an artist's yellow paint using a spectrophotometer, we can measure the amount of light that is reflected by these big objects at various rates. For example, when an artist mixes a blue paint that reflects in the blue and green with a yellow paint that reflects in the red, orange, yellow, and green, the color that remains unabsorbed in the highest amount is green, which is in the overlap region. That is because each of these pigments, when mixed together, will absorb the reflected color of the other component. And the result appears as green because apparently green is the color which is common in both pigments. So the artist realizes that the color seen is the difference between the two pigments rather than their sum. Another topic of interest for the students is the art conservation and how chemistry can come to rescue when an artifact is on the verge of deterioration. So scientists have been associated with museum laboratories for quite some time, but only recently have the curators and the conservators become appreciative of the contributions that the scientists make in order to preserve and restore art objects. One of the most frequently questions that the conservator asks is what are the component materials that are used in painting? One of those materials is pigment that can be identified using the following method. Polarized light microscopy gives information on the size, the size, the color, and the shape, as well as the refractive index of the particle. X-ray fluorescence gives information on the elemental composition of pigments. Both IR refractography and X-ray radiography gives information on the underdrawings that were quite common by the old artists. Another component of pigment is a binding media, such as the oil or varnishes or acrylic. And these all can be identified using gas chromatography and mass spectrometry. Gas chromatography essentially just identifies different number of components in a mixture. And mass spectroscopy identifies the compound essentially from its mass. Infrared spectroscopy gives information about what family of organic compound is being used in the oil or any other medium. Here I have brought you some of the examples from the National Gallery of Art that was supplied to me by a friend of mine, Dr. Sassan, who works at the National Gallery, who was a conservative scientist at the National Gallery in Washington, D.C. Here is a work of Henry Lautrec, Forgery and the Moulin Rouge. This artist actually painted on cardboard for the most part, and he did not use ground layer in this painting. He allowed the color of cardboard to appear in his paintings rather than using actual paints. The conservative scientists removed 8 little samples from this painting and analyzed it, and it proved to be oil. Gas chromatography and mass spectrometry was one of the best methods of identifying different types of oils in the sample. The 3 commonly used oil by the artists are linseed, walnut, and poppy seed oil. The analysis indicated that Lautrec had actually used linseed oil. Here are the chemical structures of what is found as a result of the hydrolysis of the oils in the mixture. The three main components are oleic, linoleic, and linolenic acid. As the chemist would say, oleic has only one double bond, linoleic has two, and linolenic contains three double bonds. It turns out that linseed oil contains the largest number of linoleic acid, largest amount of linoleic acid, rendering it to be a fast-drying oil. The more double bonds the molecule has, the faster it reacts to the oxygen, and the faster the drying oil. And a fast-drying oil happens to be a useful and desirable quality of oil by the artist. The ratio of the palmitic and stearic acid was not consumed in the process because these are non-drying oil. And when the conservative scientist wants to rule out the possibility of other binders used in the painting, they look for an additional fatty acid, azelaic acid, which is found only in the vegetable oil and not found in the animal oil. This is a work of Cosme Tora, Madonna and the Child. Here the conservative scientist was able to detect that there was a mixed media used. One was oil and the other one was egg yolk. The oil was identified using the gas chromatography mass spectrometry, and there were two tiny little samples that were taken for that analysis. One was from the red and the other one from the blue. The red portion indicated the drying oil, and the blue actually they did an experiment on the blue part. They did a protein hydrolysis, and that indicated the presence of egg yolk from the ratio of the amino acids. This is a work of Edgar Degas. Here, the conservative scientist wanted to find out, these are wax sculptures. The conservative wanted to know the composition of the wax. Again, gas chromatography proved to be an excellent method of identifying different types of waxes. And the majority of the wax that was used by this artist was beeswax, with a little bit of paraffin mixed in there as well. This is a 16th century Persian miniature painting, and here the conservative scientist, using the non-invasive method of X-ray fluorescence, was able to detect the elemental compositions found in the pigment. The black pigment, which was used in the calligraphy, was made from graphite and burning oils, essentially. The white lead was used as a ground before the pigments were applied on the paper. The red, which was a color of celebration and festivities, was found in the red ochre, the coloring component of which was iron oxide. The Persian artist seldom used the yellow pigment, but when it was used as an accent color. And arsenic sulfide happened to be the coloring component. The blue, which was used primarily in the tiles, was extracted from a precious, beautiful stone called lapis lazuli, which was also in demand by the medieval European artists. The conservative concluded that most of the pigments are actually in pretty good shape, with the exception of the verdigris green. This pigment was synthesized from the reaction between copper filings and vinegar, and it was most corrosive to the paper. In fact, this was the only pigment that required the most urgent need of restoration. Gas chromatography proved that the binder that was used in this painting was animal glue and drawn Arabic. Here is another topic of interest for the students, that is the detection of art forgeries. Forgeries are quite prevalent and widespread in the art world, particularly when you have millions or tens of millions of dollars that are spent in purchasing a work of art. It's not surprising that a false painting may be represented as an authentic one. So, the most challenging problem for the forger to solve is actually the choice of pigments. And here I have listed the history of the yellow pigment that was used by the artist from 1300 all the way through 1800. For 400 years, the artist used the lead tin yellow as the pigment. And after 1700, the nickel yellow or antimony yellow was introduced. And both chrome yellow and cadmium yellow were introduced after 1800. One of the most famous forgeries was done on the work of Francisco de Zorba. And the authentic work is at the North Sassan Museum of Art. And the curator noticed that the identical painting is actually was sold to the St. Louis National Museum. The conservative scientists decided to experiment on the pigment identification of the lemon clusters on a plate, and it indicated that in the fake painting, the conservator found that it was cadmium yellow that was used, which was synthesized after 1800. So the forger did not realize that the artist could not possibly use this pigment. That's how it was identified. When a work of art reaches a museum, historians, curators, and conservators first look at the painting. So the human eye happens to be one of the best examination methods to detect forgeries, aided by photographing it using infrared and X-ray. IR reflectography allows a view beneath the surface, such as underdrawings. And this technology works essentially because most pigments are transparent to infrared radiation. X-ray radiography, unlike IR, where pigments are transparent, there are some pigments that absorb the X-ray, and those are the pigments that contain lead or mercury, which we say in chemistry they have high atomic number, or in a layman term, are heavy metals or heavy elements. This is an example that illustrates the transparency of pigments towards infrared radiation. The top left is a photograph of charcoal drawing in the visible way. At the bottom left, the artist has intentionally placed several layers of paints to cover the drawing. And the image on the right is actually an infrared reflectogram which shows the underdrawing, and that indicates that the pigments the paints and the pigments were transparent to the infrared. What was absorbed by the infrared was the underdrawing charcoal, which essentially absorbs the infrared and reflects against the white background, and that's how the image becomes projected. Here is yet another example of the work done by Francisco Goya. Here is a photograph of the painting taken in the visible light. As you can see, there are no indications of any hidden image. The top right is an infrared photograph of the infrared image of the painting that shows, if you look closely, the eye and the eyebrow. This indicates that the artist used pigments that absorb the infrared in the hidden image, again reflecting against the white background to make that image visible in a visible way. The bottom right is the X-radiograph of the painting, which essentially shows a more complete picture. You can see the old wise man with a beard, and that was the hidden image. And that shows that the artist used those heavy metals or the elements containing the high atomic number that absorb the X-ray, and it blocks the blackening of the film which is placed behind the canvas, and it will appear as light areas in the X-radiograph. Here is another example that demonstrates the transparency of pigments towards X-radiation. The photograph on the left is a photograph of the painting by Pragma. The one to the right is the X-radiograph, or the same painting, indicating that the pigments that was used by the artist to in the hidden image were those made up of lead and mercury. And again, after the absorption of the X-ray, they essentially locally block the darkening of the film which is placed in the back, and they will appear as light areas in the X-radiograph. Well, this is, I just looked at some of the lecture topics that I covered in class, but there is a laboratory component. I won't have time to go into all the experiments. I just I picked some of the laboratories that are done by the students, one in painting, one medicine, and one textile. I have some examples of it here on the board you may want to look at later on if you're interested. The painting experiment we do is actually one of the old and ancient technique of painting called fresco. And it's a very simple chemistry. They take plaster of Paris and they suspend it in water and they basically put it on a tile, and that acts as a support, the ground, and the binder for the pigments in the paint. As the binder, as the plaster is drying or reacting with the carbon dioxide in the atmosphere, you begin to place the pigments. You basically paint it on top of the layer of the fresco, and then the pigments essentially penetrate through the fresco and they're permanently engraved in there. That's how it remains there for decades and centuries. Here's another experiment involving metal etching. They etch copper plate using nitric acid. What they do, they cover a copper plate with wax, and they engrave or inscribe a work of art on the plate, and they put that inside the nitric acid bath, and the exposed copper reacts with the nitric acid bath. And the whole etching completes in 10 or 15 minutes, and later they just remove the wax using an organic material, or they just burn it off. Here's a picture of two of my former students during their tie-dyeing t-shirts with indigo. I believe that this course is pretty much suited and tailored for a new program that the art department here at QCC is initiating. Gallery and the museum studies. The chair of the art department, I don't know if she's here today, Dr. Joanne Wayne. She's actually initiating an articulation agreement with Queensborough to start this program, and then when the students get their associate degree, they can transfer to Queen's College, or if they choose, they can go to the School of Conservation at NYU. They also offer a 4-year program that incorporates, the experiences with conservation that combines the practical experience in conservation, the curatorial, historical, scientific studies, and the construction of work of art. They have some career opportunities once they complete the 4-year bachelor's degree. They can do internship during their college years at the Metropolitan Museum. They can work in departments such as the curatorial conservation department or work in the administration. And they can apply for full-time positions in the Museum of Modern Art, which offers a program, a preventive conservation program that allows the students to get hands-on experience with restoration in the conservation department. So in conclusion, I hope that I have convinced you that the scientists have made enormous contribution to the analysis of artwork. Some of the various techniques that I talked about, namely gas chromatography and mass spectrometry, is used in order to reveal the binding media such as oil, acrylic, or varnishes. And the structure of pigments and their physical properties can be analyzed using the X-ray fluorescence as well as the polarized light microscopy. We also saw how the interaction of special type of light such as X-ray and infrared that penetrated deep into the painting allowed viewing the undertones when it was totally invisible in the visible portion of the electromagnetic wave. I'd like to acknowledge Mary Virginia Orna, whose book we're using, that we have been using for a number of years. And I'd also like to thank Professor Sassan that I got some of the slides that I used in today's presentation from. I also used some material from The Science of Painting by Stanley Taft and James Meyer. I'd also like to thank Dr. Suzanne Lomax from the National Gallery for providing me the slides that I talked about, the work that she had done in the conservation laboratories. Here are the students that have nothing to do with the arts. These students worked with me in the lab over the years in the chemistry of natural products. I talked about Paula and Julia. My husband, Sadia, worked with us, Dr. Swans, the paper that we published in Pedagogy on the chemistry of chemical rearrangement. Both Pegorian and Sassan are presently working in the lab with me at Queensborough. Here, this is the X-ray collection of the chemistry department. Let's see who is who here. You can see the darkest area is actually in the brain. We tend to have a lot of mercury in our head. This is the actual picture of all the people in the chemistry department. I really thank them for all their support. And I'm certainly not the only one who does research with students here. They all do fantastic work involving students. I also like to recognize our chief CLT, Peter Irwin, who is really helping out a lot over the years, trying to devise and design the laboratories from the beginning, the inception of this course. I also like to recognize Bruce Montalbano, who I've given him so much trouble with my last-minute request about the chemicals that I needed to use in these experiments. I also like to, last but not least, thank Queensborough Community College administration for their continued support of the student research project, for supplying us with the state-of-the-art technology of the infrared spectrometer, gas chromatography, and mass spectrometry that I talked about today. And just like to leave you with some of the excerpts of the students' evaluations. You know, the students get to evaluate us when we finish the course, so I have cherry-picked some of their comments. One student says, this class definitely opened up a whole new train of thought when it comes to art. I found this so more interesting because it's being applied to my field. Dr. Karimi definitely explained things well and made things interesting. I also like the use of visual aid. Professor Karimi made a very dull topic interesting. He taught us how to apply concepts to the real world rather than memorizations. He made chemistry lectures clear to me. This class was cool. I actually learned something, and I'm not that great in chemistry. I love this last one. I hated chemistry before. I hate chemistry now. I was very understanding of it because of Professor Karimi. His teaching method is extremely productive and conducive in some sense to my education. I thank him. This is the last chemistry questions.
I was told by a hardware store man that ordinary glass has acid in it, but I don't necessarily believe him, because on the internet I see they're selling UV glass, and they don't mention anything about that they've gone to trouble to make it acid-free. So what's the scoop? Is there?
I've never heard of acid in a glass. I know that there are silicates and aluminates in glass, and there are other compounds that are used.
What was the question?
The question was, are there any acids that are used in glass? And to the best of my knowledge, I don't believe there is. I've never heard of acids being used in glass. They're just a bunch of silicates and aluminates for the most part. Any other questions? Yes?
This is a very stupid question. I don't have to ask it. because it was bothering me through your whole lecture. When I studied arts, I learned, I learned about the light of primary chemistry, red, blue, and green. And
Those are the primary colors of light.
of light. But when I studied art, we learned that the primary colors in pigment were red.
You missed the first part of my lecture. Go ahead, please.
We learned that yellow, blue, and red are the primary colors because you
It's cyan, magenta, and yellow are the primary colors of pigments.
Right. But you said you gave us 3 different colors, like cyan and participated herbs.
From the combination of the primary colors of light or the pigment.
From the prick, you said it was the prayer color of the pigment. And you get
Actually, from mixing the primary colors of pigment, you create the primary colors of light. So when you add magenta to cyan to yellow, you produce the red, green, and the blue that are the primary colors of light.
But what about this red, yellow, and they used to give us a color wheel, and they'd say these are the primary colors. If you want to form any color, all you need are these 3 colors: red, yellow, and blue.
Is there an artist in the crowd?
Sorry, they never have the color wheel. You can combine the red and the yellow to make, the alternate colors. But you got
You mean the secondary or the tertiary colors, right?
Yeah, they gave them.
I didn't talk about that too.
Yeah, primary and tertiary.
I don't know about it. I'm not sure.
I have a different question, Sassan. Could you say something about, for painters, how the development of commercial chemistry would probably change the work of a painter? So that, for example, early Renaissance painter would probably have to create their own pigments and create their own paints, as opposed to someone in the late 19th century who might be able to buy a lot more things already made.
Actually, a lot of the new pigments that the artists use are synthetic pigments, as you know. And one of the advantages of the synthetic pigments is that they're pure. When the artists used to use the old pigments, they were mixtures of a bunch of compounds that they could not isolate or separate. So one of the main advantages of the new synthesis, that inorganic synthesis, I should say, brought about was the purity of the new pigments. Any other questions? Yeah.
I'm more interested on the flip side of the forgery part that you're talking about a little bit. And so you walked us through how chemists have been able to identify the generations of yellow, for example, right? So now that we know that, can we go back and I can talk to my forger friends and we can do and make either synthetically or naturally that original, I can't remember what it was called, with the tin.
Right.
Can that now be done so that it complicates the notion of forgery and authenticity?
I'm sure the forgers, you're giving some ideas to the forgers. There is also, I'm not really that familiar with if forgeries, for example, the new forgers can actually replicate, the exact and identical artwork that the original artist did. But you're right. The forger needs to know the history of the pigments. They have to be fantastic artists.
So I'm going to have a lot of trouble.
Yeah. Yes, David.
What about the under images that you showed in a couple pictures? I was just curious if, what they were doing there. Were they purposely placed there by artists?
Apparently, this is in my readings. The old artists, because canvases were expensive, they didn't want to just paint something and throw it away if they didn't like it. So what they did a lot of revisions. Old artists did many revisions on paintings. That's what happened in the old days. It doesn't happen too much these days. Yeah.
One other thing, that they claim that ultraviolet rays can damage artwork. That's supposedly the reason for the UV blocking glass. So Could you shed any light for us on the UV action on?
But ultraviolet light has a lot of energy. Its energy is higher than the visible light. So you will damage the work of art using UV light. That may be why you need to protect it against.
The question you asked.
Oh, the question was can UV damage the work of art? Is that right?
More or less, how does it?
Just because it has very high energy and it can, well, the ultraviolet light can excite electrons, as we say in chemistry or physics. And by exciting electrons, you bring them from a ground state to a higher energy level. And you can also deteriorate the compound using that, so the compound can lose its identity that way. Yes?
When you restore works of art, is an art restorer, is an art conservator looking to replicate whatever was in the original compound?
I'm sorry, I didn't hear the first.
Sorry. If you're restoring a work of art, are you looking to replicate whatever was in the original work of art,
Exactly.
or is there sometimes a project to synthesize some new compound that may graft onto what's already there without destroying it?
Right. Actually, the work that I showed you that Dr. Sassan was doing, she worked on those paintings prior to their deterioration. So they wanted to find the composition of the paintings. And in case if the work required any restoration, they know exactly what it was made up of. And they can use that same exact chemical to do it to the restoration.
What's the difference between a restorer and a forger? One is legal, the other one is not, right? Well, I think this has been wonderful. This, it's wonderful to be the president of a place where you have faculty like this, and it's wonderful to be able to show it off. And it's more wonderful to show it off to our own family, which is a wonderful thing. So I am thankful for what you have done today. I think that has been most interesting. And I know that we have refreshments outside, and I know that other questions can be asked as we invite in coffee. We don't serve liquor, but it's a wonderful thing. I still don't know how you get those students to do original research as freshmen and sophomores. And I will continue to ask you that question. I think it's fascinating. I keep saying that there's something magical going on in the chemistry department here, and now it's spreading to the biology department. And it's a wonderful thing to be able to really, really believe in the students the way that this faculty members do. And this one?
Yeah, just one question.
You have to speak up.
You mentioned something about that. During the lecture, you mentioned something that green pigment is toxic to the painter.
No, that particular green pigment that was used using copper fining and vinegar. Vinegar, in vinegar you have acetic acid, and acetic acid is what ate up the paper, and that's what the conservator spent the time trying to repair.
Because I was just wondering why it was toxic.
It wasn't toxic; it was just corrosive to the paper. That's right.
So it's not toxic to the paper.
It's corrosive to the paper. It made a hole in the paper.
One more. Music control this crowd.
3 points. A lot of the artists in the past became addicted because they used lead, and so you have a problem with addiction. Since the man was asking about forgery and pigments, one of the pigments that's strange was called mummy yellow. At one point in the 19th century, when they first started excavating all the mummies of Egypt, they would grind them up and turn them into pigment. Eventually people realized what it was made of and it became abhorrent, so they stopped using it. The third thing is that physiology also plays a role. For example, with El Greco, with extremely long faces, they believe that he painted the way he did because of the eye problem.
Why don't we thank Dr. Karimi?